Thank you for the introduction and invitation. Yes, so many of these words, maybe except algebras, don't really sound very familiar to many of you. So I decided to make this talk very accessible since I'll be here for the next couple of weeks. If you have many more questions, I'm here. So it's more like an introduction to this program of studying conformal blocks, which I'll explain what they are. They are some natural vector spaces, which originally in the end of 80s and 90s were studied attached to Lie algebras. But there is sort of a, I would like to say that it's more natural to see them attached to vertex operator algebra, which can be seen as generalization of Lie algebras. And so I want to say something about program that aims to understand the properties of these vector spaces, which then become actually sheaves on appropriate moduli spaces. And so in this 50 minutes, 1 hour today, I'm going to go over an overview of what's been known, what we've proven, and maybe what will be the future path. And everything I'll say today is either attributed to other people, and my joint work will be joined with Angela Gibney, Nicola Tarasca, and Danny Krashen. And I may say something about other work in progress, but we'll see how the time goes. So what are these mysterious conformal blocks in the ideal world? So the ideal scenario what we have that spaces of conformal blocks, I'll just write CV, define vector bundles on the moduli space of genus G n-pointed curve. And these vector bundles actually behave nice in which behave nicely, let's say, under tautological maps. So this is essentially the best case scenario, what we would like conformal blocks to be. So they are those vector bundles, depending on some representation theoretical data that I will say. They live on MGN bar. And we know that there are various tautological maps from MGN bar to MG prime and prime for getting points, clutching points together. And so these vector bundles are not just isolated, like there's a vector bundle on MGN, another one on MGN plus one, but they sort of talk to each other in a very explicit way that makes it possible to compute their rank and their Chern classes. And Dragish knows something about it. So for the Lie algebra. So I want to look at this thing and think, okay, maybe these are objects we might want to understand. I always want to understand MGN bar, perhaps. And in general, if we, like many of us, or maybe all of us are algebraic geometers, having vector bundles is one of the good ways to produce maps, perhaps to other projective varieties if they have some positive properties. Right, so this is a bit the ideal scenario, and we will see that the ideal scenario is not always going to be true. And so the goal is how to get around. So let me just try to, before starting giving a definition of what these conformal blocks are, I want to say that one of the goals, perhaps, of studying these conformal blocks in this more general setting is related to, well, the terminology comes from physics, and I really don't understand the terminology, first of all. So please don't ask me why these things are called conformal blocks. This is the name that they were given to them. So I will actually cannot be able to answer this question. But they're related to conformal field theories, and in particular, these properties here, or this sort of the ideal properties, should tell us that the conformal blocks define what's called modular tensor categories, modular tensor functors. There is a way to phrase these properties in a more categorical way. They are derived version of conformal blocks. And this is a bit why one maybe wants to go to the vertex operator algebras instead of staying only in the Lie algebra setting, where only fewer phenomena can occur. So let me start answering this question, that what are conformal blocks? And I want to start in the Lie algebra case, meaning where instead of considering vertex operator algebras, I instead consider the easier case of Lie algebras, which I hope everyone knows what they are, but you can think about matrices where you can sum them, and then the operation, you take a commutator. So my favorite Lie algebra is SL2, or SLN in general. So what is this? So conformal blocks, as I said, they are some spaces. Sorry. So there are some spaces, vector spaces, which are attached to what I like to call decorated curve. So what is a decorated curve? I will just draw something as a Riemann surface. Just why not? Maybe I have a, well, let's not do the nodal case, yeah. So I'll say it in words, and then I'll write down exactly what a decorated curve for us is. Essentially a point of MGN bar, where to each point you put a representation of your Lie algebra. So I'm decorating, I'm marking my curve instead of just marking by points. Every point sort of has a representation theory interpretation. So I can encode this description by saying that I have a geometric input. So the geometry I have curve. So I have a point, so I have a fixed curve, which can be smooth or can be have at worst nodal singularities, and I have n distinct order points, which must be smooth. This is my sort of underlying curve. And then I have what we call the representation input, like the decorations. And in this case, so I'm in the Lie algebra setting. I start with a simple Lie algebra. Can always think of, let's stick with SL2 or SLN, traceless matrices. I fix L, which is a positive integer. This is more like a technical conditions called level. And then I fix M1 to Mn, the decoration that I give to this point. These are simple, maybe finite dimensional G modules. And maybe I write here in parentheses of level at most L. So this is some technical condition that will restrict the category of modules that I have. For SL2, this just means that my modules have bounded dimension. And for SLN, you can just write down this in terms of Young diagrams. And in general, what this level condition tells you is you have some nilpotency. So you don't want to take representations which are too big. Every element of G, which is nilpotent, after you apply L plus 1 times, it acts like 0. Right? So in particular, there are only finitely many options here. There is a finite set, and so what I'm saying is that there is a way to take this data, which is not small, and produce a vector space, which has sort of a sensible, which is not just, I remember M, right? This would be a way. But it's something that varies in family nicely and maybe tells us something about the representation, the intertwining between the representation theory. Oh, wow. and the geometry. So how do I define conformal blocks? I want to give you the flavor of these definitions now, because for vertex operator algebra will be essentially the same, or the same idea. And so this is sort of the baby example. So the idea is that these conformal blocks that are usually, now we'll call them. So the space of conformal block, sorry, I cannot push it down. Associated with this datum, that it's often denoted as a V dagger or some letter dagger. And the dagger is because it actually arises as a dual of another space. All right, so this is a dual of another space, which is called the space of coinvariant. And the word coinvariance already is more clear than conformal block. It arises as quotient of some space by an action of something. So what it is, oh, I see, I should have maybe started with the other word. Sorry. So what this space is, this is a quotient of, let me just write this, thickenings of M to CT. I will explain in a second what I mean by the algebra. And we call it LC minus P GL, which the algebra needs to encode to datum the fact that I have a curve and some points, where at the points I have the modulus M, and needs to encode how G acts on M. So the idea is that we have these modules that I can imagine being at the point. But what I want to do is that I would like to sort of spread them a little bit to the puncture disk around that point. So that's what I mean by thickening of M to CT. So CT I can see as being related, let's say, just put an arrow, to the puncture disk near the point. Right, so I can do, and the other point. Sorry, I don't want to cover this board. Right, so I can sort of spread them out. There is a standard way of doing this. So from being modules of a Lie algebra over complex numbers, as I said too, they became actually a representation of unaffine Lie algebras. So these thickenings of M, blue, sorry, these thickenings of M, let me call it, sorry, I want to use the same notation. So let me call it ML. So these are representations of now a bigger Lie algebra. So I first extend the scalars from constant coefficient from complex numbers to I allow Laurent series. And then I actually take a central extension. It's like a universal central extension. And the level is because I require the central extension to act by L. So there is sort of a canonical procedure to start with, and this is where I use the level, to start with simple modules over G and induce them up to what's called integrable and irreducible modules. And so, but I really want to think about this really geometrically as living in a small puncture disk near our points. And perhaps, and I do this for every of these M, and I can take their tensor product of them. So this is where like the numerator, like I'm quotienting something which is very local. So this is local. And I want to then, if I want to have something that perhaps sees the geometry of the curve and not just a lot of disks, I need to also encode some global information. And this is encoded by this Lie algebra. The Lie algebra I take in this case, I'll write it. I take, instead of extending my Lie algebra to the formal disks, I extend it to the puncture curve. And it turns out that this is didn't tell you what the bracket here. The bracket is not component-wise. There is a cocycle. The cocycle vanishes here. The cocycle is given by residue, so geometry tells us that the cocycle will vanish. This is a list of algebra, and I take this invariance, this covariance. So if you want, this construction should remind you, looks like, to me, the first time I saw this, reminded me a bit of an H1. I have something, if you want this, the numerator takes care about the puncture disk and actually sees the whole disk as well in the way in which you induce it up, and then you're even quotienting out by the open. So there is a precise way of connecting this to this description. And so this, now we sort of have a better understanding of what these conformal blocks are. And from now on, I will just say, probably just focus on coinvariant. So I might just, by mistake, say conformal blocks, but every time I mean coinvariance. And I will denote by V. And then, of course, I need to decorate everything this space, right? So I want to repeat this. Right, so this is the definition. Oh, sorry. Right, so this is the definition that of coinvariance. And if some of the datum are clear, I might drop from the notation. Are there questions at this moment? Oh, I did. It's the induced representation of this affine Lie algebra. So if you want, this definition is the following. So you first take M. No. So you first take M, and you see that G of T acts there by sending T acts by 0. And also, and C acts by L. Or maybe if you want, sometimes people like to take an element here, but multiplication by L and induced up. And then you induce up. Let me call this the algebra G hat. So you do an induced representation. Turns out this is really not irreducible, so you need to take a portion of this. But it's the usual Verma. It's a sort of a parabolic induction, or just induction from a sub Lie algebra. But what I'm interested, the conceptual thing I would like to say is, we have something that is comes purely from the representation theory that lives on disks, and the geometry is all encoded in this Lie algebra. Okay. And a priori, maybe something to observe that sometimes I get asking talks is, here I sort of fix a coordinate, but I never told you that my curves were just curves and points, not coordinates. There is actually a bit of work to show that your vector spaces do not depend on coordinates. Okay, but maybe the upshot here is that we are indeed in the ideal scenario in this case. So I will just write initials. So Tsuchiya, Ueno, and Yamada in 89, and then Tsushimoto later. Tsushimoto proved the independence of coordinate. Showed that indeed, if you fix your G and L, and also M1 to Mn. So you fix your representation input. And the most important thing is that you fix G and L, which really determine the category where you're extracting your representations. Then, by associating to each pointed curve CP these vector spaces, indeed defines a vector bundle on MG and bar with a projectively flat connection on MGN. So on the open part, actually, this vector bundle doesn't really have an action of the tangent bundle, but the action is well defined. It's not flat. It's flat up to constant. And this fact that they behave nicely under tautological maps is one of the key features of this spaces, which actually help us showing these are vector bundles. Now, at the moment, you might believe that the definition is functorial, right? I could have taken a family of curves, do this construction. Everything is functorial, so we'll define a sheaf. This numerator, this module, dimensional. Already the fact that this defines a coherent sheaf is not obvious. And then I'm saying it's actually a vector bundle, not just on MGN, where, well, if you have a coherent sheaf with a flat or projective flat connection, you'll be fine. This also is true at the border, at the boundary. And this is encoded, and this is the reason why this holds, if you want, is because the sentence tells us that if I start with the space of conformal blocks on the boundary, there is a way to relate it to other spaces of conformal blocks on the normalization. And so I have control. I can translate the problem from the boundary, where I don't know what's going on, to the open locus. And actually, I can say something more. I can essentially say that conformal blocks attached to a deformation of a curve, like a versal deformation, is just a trivial deformation of conformal blocks. All right, so specifically, I want to write down these two properties. And I will draw it in pictures, if you let me. So suppose that I dropped my Riemann surfaces picture to prefer the usual more algebraic geometry picture because it's easier with nodes. So suppose that I start with this. So this is a curve where I have some points, a decorated curve, right? And I said, we know how to define this space of coinvariance. Now, what we've learned in algebraic geometry is we have a nodal curve. Maybe you want to take the normalization. Right, so many things on a nodal curve can be described as things in the normalization plus some gluing. Right, so I can take the normalization of your curve. So this is now, again, marked by my old points. But now I have two extra mark points. So this is sort of a decorated curve, but not completely. Like I have some points which are decorated by modules. And then I have these two new points, which at the moment are not decorated by anything. So I cannot really associate conformal blocks at this moment. Well, but what I can do is, what one of these properties tells us, is that if I take, let me just write, oh, I didn't give a name. Well, this is maybe the set of representations of G of level at most L. So if I decorate one point with W, I decorate its friend with the dual. And it turns out that if I take, there is a canonical map that actually decomposes the vector bundle on a nodal curve as sum of vector bundles on the normalization. Right, so this is the first thing that it's a property that not every vector bundle has. Right, so this nice decomposition. And if you already know that this was a vector bundle, this already tells you that you can compute rank inductively on the genus. So you're only reduced to compute the ranks of on P1 with 3 mark points. Okay, so we say M1, 2, and 3. So once you know this rank, if you already know they were vector bundle, you know the rank of everything. But as I said earlier, so maybe this is called the factorization property. The other key property that we have that goes under the name of sewing, because it can sort of describe more topologically as how you can sew some curves to get other types of curves, says that a similar statement is true when instead of taking just a curve, I take a curve over a small disk. So let me try to do it. So I have now a family of curves where the central fiber is nodal and the generic fiber is smooth. And then I still have my decoration. And one can show that this, again, simply decomposes, or yeah, so maybe let me just write this in this way. Let me just write this in this way, okay? So what I can do is that essentially here, I have a non-trivial family of curves. I have a deformation of my nodal curve, and essentially conformal blocks don't see this operation. Like they just trivialize. So these are vector spaces over C tau. Right, so this is sort of crucial to show that these are vector ones. Right, so these two properties, and again, there is a canonical map that one can describe, and maybe combining these two descriptions, this is the same here. Right, when we are now marking these 2 extra points. I will not. Now, I wanted to explicitly write down these properties because those are hard to generalize in general. But before going to doing the jump from Lie algebras to vertex operator algebra, I want to state other properties of these conformal blocks. Other questions before I do that? Okay, so some of the properties I wanted to describe are some are, I would say, more surprising than others. So as I said, first the rank can be computed inductively. So maybe more properties. Actually, it's the Verlinde formula. Gives the ranks. And this is like a way of patching together. You do induction, and then you do a lot of representation theory to put everything in a nice formula. So if you ever want to compute those ranks, there are also Macaulay packages that do it for you, some cases, but you potentially, you just can't do it. Once you know these numbers, and these numbers are not there. These are just on, it's representation theory, and you can just do it again with a computer. In SL2, I can tell them. I can tell you. Second, which perhaps is surprising, is that now I want to consider conformal blocks. So now I'm really in the dual space. And I take now the trivial representation, right? So this C is the trivial representation. Now there is a isomorphism. So there is actually, like to say, like a cohomological interpretation of these conformal blocks as spaces of sections, just right here, of line bundles on the moduli space or moduli stack parameterizing principal G bundle, where G is the simple and simply connected group whose Lie algebra is G. And in that case, the Picard group is Z, and I take the positive line bundle associated with L. So in this case, we can see that the level that before maybe was mysterious can be seen as being very geometric realization at which line bundle you take. And actually, this factorization that I described, so this could also hold true also for nodal curves where you really need to take the stack, not a moduli space, tells you that actually you can decompose this space into direct sum of global section of line bundles on parabolic bundles. So one can enhance this also to when you move from C to maybe more a non-trivial representation, but you have to pay the price. Then now you have parabolic bundles, and you can put maybe the Borel at your mark point here. Okay? And it's similar. The line bundle here, there would be a way to get the correct line bundle from the representation here. And perhaps this was one of the reasons why many algebraic geometers started thinking about conformal blocks, because I think in the, well, for SLN, this is attributed to Boisville and Laszlo, so Sorger worked on this. And in general, there were no methods to compute the dimension of this space. Well, first of all, there is no reason why this should be finite dimensional. I mean, if you restrict perhaps to the moduli space, but just think at the stacks level, there was no reason to do it. And there were some partial results. I think for SL2, Michael Thaddeus had some results in that direction. But all the finite dimensional methods were not able to give you a description of this space. When I say finite dimensional methods, I mean without passing through this infinite dimensional representation and then coming back. So you do this detour through representation theory of complicated objects to have a beautiful realization of these spaces. Now I think there exists some finite dimensional proofs, but I don't know the details of those. Okay, and then the last two properties that I want to say is that we know all Chern classes of these sheaves on MG bar. This is work of Dragos and co-authors, which heavily uses the projective flat connection, the fact that actually we can explicitly describe it in terms of the algebras, and uses classification of semi-simple homological field theory. So that's sort of a important another property that these sheaves satisfy. And the fourth is that actually on M0 and bar, so if I restrict to genus 0, these sheaves, these coinvariants are globally generated. So one can ask, if I have globally generated, I can then do some geometry, construct some maps out of MG and bar. And so have been some works in that direction. So maybe what the dream would be, let's take these two blackboards, replace simple Lie algebra, replace GL with a vertex algebra V, M with modules, whatever this means. Does this go through? Is there an abstraction? Okay, so that's sort of the goal. And the reason why this makes sense is because essentially the only thing we need from GNL to make this work, for the construction, are properties that can be described purely in terms of vertex operator algebra. So I will not have time to tell you what a vertex operator algebra. And rather, I want it wouldn't make sense because the definition is very dry and it doesn't convey a lot of idea of how they look like. But what instead I can do is I want to make a part of how you can start with GL, like the Lie algebra in a level, and maybe construct the vertex algebra. there, and then do a general case first. Are there questions while I raise? So how do I go from a Lie algebra? So let's see. So I'll just say quickly what vertex algebras are. So we have a vector space, which is graded over the natural number. And the word algebra should tell you that there should be some operations there. It's not just a vector space. It should be some multiplication. But if you think about, like, in the Lie algebras, you have a Lie bracket satisfies some axioms. If I have an associative algebra, I have another multiplication satisfying other axioms. If I have a Poisson algebra, I still have maybe other operations. So in this case, to every element A of V, I want to associate actually a family of endomorphisms, which are sort of attached to N. And depending on N, they need to satisfy some requirements, some axioms, which essentially relax the associativity condition or commutativity. So there are a lot of axioms, but the idea is that I would like you to think of a vector space where to each element you have a family of endomorphisms. Right? It could be that, maybe I'll say something totally wrong, but take a ring or take a vector space and take a ring and then to an element you associate multiplied by x or multiplied by x squared or multiplied by x cubed. You can do this for every positive element. Right? So there are other operations that satisfy different axioms. An important thing for us is now I want to tell you how, if you start with GL, you can cook up a vector space. And maybe I can tell you something about these operations. Yeah. Yeah, so that's how the notation. So the right way in which they interact is that, I need better chalk. So this is an endomorphism of degree -n - 1. That's how you encode the information. Right, so that's a way in which you encode it, and there are some other axioms that tells you this is going to be a Laurent series. Yeah. Yeah, because that's the grading. Oh, it's when you write the axioms, it's much easier to write with the shift. I don't give you the axioms, so it's, well, you don't see the axioms, so it's hard to digest them. I mean, I find it much easier to work with this. I don't know, that's how the literature, I mean, in the literature, you can also find them differently. So depending, sometimes if the elements here have degree n, there's degree k, they will write z minus n minus k. So there is a way in which you can write. Yeah, I mean, I can maybe say something more later, like this. I mean, the reason is really the residue theorem. So if you take an element, often you take an element in V tensor Laurent series, and then you take the residue of this field, then you get really A of n, which was just A. That's the reason. So I can, well, this is a bit on the side, so I don't know if this is interesting now, but there is a way in which this notation makes more sense, but it goes in the background there, and it's maybe too specific to do that. But yeah, I can say something more about it. But maybe what I want to say is, at least I want to say how, if you have a Lie algebra in a level, you could have at least a vector space, which is graded, and is essentially what I wrote before. So you do, before I use this notation, you take the trivial representation, you induce it up to this affine Lie algebra of level L, and then you take, you might take this irreducible quotient if you want a simple vertex operator algebra. Right, so if you think about it, let me try to write it. So this is gonna be maybe C at level 0, right, at degree 0, where you have your maybe highest weight vector there. And then you're going to have G to the -1 times tensor CV0 at degree +1. So often the degree is given by degree of poles because we are inducing in that direction. And then you can sort of keep going, having elements of higher and higher degree by taking more elements in the universal enveloping. And so a feature that we see here is that at degree 0, we only have a one-dimensional object. And there is a highest weight vector, and this is always something we have. So V0 is always, there is a favorite element called the vacuum vector, which sort of plays the role of the identity, which here is played by the highest weight vector. And in this specific case, we can see that in degree 1, so if I call this is usually denoted LLG, the affine Lie algebra, the affine vertex algebra, simple affine vertex algebra. Turns out that LLG1, if you want, is isomorphic to G. Let's say it's a bijection with G at this moment. So there is a way in which the degree 1 component recovers your Lie algebra G. Now, there exists vertex algebras where the degree 1 is just 0. So not everything comes from the algebras. Those coming from the algebra are very special, and they actually behave much more similarly to this one. But there are examples such as the monster vertex algebra that doesn't have anything in degree 0. In degree 1, sorry. So we're really beyond the case of the algebras. And here, maybe I didn't tell you these operations. They're a bit harder to compute, but maybe let me tell you that if I take this element, like, so this element belongs to our vertex algebra. This is a degree 1 element. And I want to compute what is its endomorphism. This is an endomorphism of this space, and it's given by left multiplication by this object here. So you see that there is some nilpotence condition that are verified, which are part of the axioms that I didn't tell you. But as soon as you take elements not of degree 1, the description of this endomorphism is much more complicated. There are theorems that says that essentially this vertex algebra is uniquely characterized by this property and the axiom. Everything else follows. So really, in this case, the Lie algebra tells you everything about the vertex operator algebra. And not only our modules, so here we have our modules on this side, which I said belong to PL plus, so I use this notation. This means dominant weights of level at most L, which are really simple representations of level at most L. This really corresponds to the simple LG modules. Corresponds by sending M to M tilde L. So when I said thickening before, really meant I'm not anymore in Lie algebra land, I go to vertex operator algebra land. Okay, so this is the, and these are the only simple objects that I consider. There are different categories of representations one may do in the VOA land, but we are going to be interested in those. And so this, I wanted to give this example this shows a bit how you can go beyond the Lie algebra case, but without being too technical. And one thing that I want to say, but maybe more for expert, is that what I said so far is called vertex algebra. And the word operator means that I have the Virasoro Lie algebra acting on V. And this is really the link to geometry. The Virasoro Lie algebra can be seen as, so it's an extension of the Witt algebra, and the Witt algebra are deformation, are like derivation of the puncture disk. So this is it's related to deformations of curves. So this action of the Virasoro is sort of the responsible of the connection, this projective connection that I mentioned before, and is responsible. So that's why we can do conformal blocks for vertex operator algebra, not just for vertex algebras. In the literature, these are also called conformal vertex algebra. And in this case, writing down how this representation is, this is the Sugawara construction, Segal-Sugawara construction. So you can explicitly write down what the elements of the Virasoro act explicitly. And one can see very nicely how the coordinates play a role there, and dropping coordinates give you introduce this projectivity. So now, sorry, I'm a bit out of time, or still have some minutes, 10 minutes. So now that we know more or less what a vertex algebra is, so maybe I convinced you that we still have the numerator of coinvariance, and the hard part is to find in this Lie algebra. Right, so let me just say at this point, what we have is that if we hope to construct conformal blocks or coinvariants, and let me just take 1 point for simplicity instead of taking many, associated to a vertex algebra and a module, maybe now I call this again M, then what we know, if we want to mimic the usual construction, I should quotient out M by some Lie algebra that encodes the geometry, but also how M is a V module. Right? So I know I didn't tell you what a V module is, but intuitively you can imagine it's an object on which V acts in an appropriate sense. Right? So the hard part, which is how to define this object, so that essentially it varies in family. So it's a functorial way. And hopefully you obtain vector bundles. So since time is a bit up, let me just say that the definition, there is a way to do so. Perhaps it may be more than one way. And so Frankel and Vance V constructed over MGN, but not on the nodal case. So considering the nodal situation is more complicated, Nagatomo and Tsuchiya, they consider nodal curve, but only in the rational case. And myself with Angela and Tarasca, Nicola, we completed the picture, extending to MGN bar. And this is true essentially without, we have to put a little bit of restrictions on the VOA and the modules, but not that much. It's quite a general construction. If you perhaps fix a coordinate, dropping coordinates is always hard. And furthermore, what we proved, the next result is that if, we just say theorem, digit is me, Angela, Nicola, is that the dream situation that I had before, the ideal situation, is true for C2 cofinite and rational VOAs. So I want to say something about this condition. So first of all, the blue part on the board tells us that we can define quasi-coherent sheaves on MGN bar, and there is a projective flat connection on the interior. Okay, so this is what the blue part tells us is that we have is a quasi-coherent sheaf on MGN bar. Then C2 cofiniteness, as the name suggests, is some finiteness condition that one can naturally impose it on a vertex algebra. It corresponds to, so there exists an associative algebra governing the representation theory of V, and the C2 cofinite implies that this algebra is actually finite dimensional. So there are finitely many representations, if you want. So this C2 cofiniteness, this ensures coherence. Actually, this is resulted we proved with Danny Krashen. So with Nicola, first, we didn't realize that C2 cofinite was enough to imply coherence on MGN bar, but with then Danny later, we realized that that was enough. And rationality, again, maybe the terminology suggests that it has to do with the category representations. And indeed, what rational means is that there exist finitely many simple representations of V, finite simple modules, and that the category of modules is semi-simple. So everything is built out from these simple breaks. And so in particular, if you remember the factorization that there was before and sewing, where I had a direct sum and I sum over the simples, I can still make sense of that. The modules are closed under taking the category is closed under taking the dual. So those statements, first of all, make sense, and we can actually prove that they hold true, right? So it's the ideal situation is true, and also factorization and sewing holds true. These two conditions that actually tells us that they are vector bundles. Now this is great, but in the world of vertex operator algebras, rationality is really too strong condition. Like it's really too strong. Just as an example, there is a way in which one can define sort of higher coinvariance. Like this would be like a zero, this would be zero chiral homology, and there will be higher chiral homology. And the conjecture is that this, if the vertex algebra is rational, this higher chiral homology vanish. So you won't go really, you would like to go beyond the rational case, right? So what we are trying to do is the final goal maybe, so the desire is to drop rationality and hope, hope to get, let's say, some nice sheaves on MGN bar. Again, the problem is all at the boundary. Sorry, maybe. The problem is all at the boundary. If you impose C2 cofiniteness, everything is a vector bundle on MGN. The problem is always how to consider this nodal curve. And the methods that have been developed in the past, and the main properties of this factorization and sewing, we have factorization. There is a way in which you can phrase it. Sewing, we could find some conditions to essentially rephrase this in a completely algebraic ways. But I will not have time to say now, because I only have 4 minutes. And instead, let me just say something. I had a list of properties which I don't know which board they were, and I want to say which of those properties still go through and which others do not, right? So, but I'm happy to answer questions or whatever. Huh? There are also CN. So the way in which you define this condition is that you define a sub-vector space of V, which is like things spanned by elements in type A2. And then you can do for every n. So there is C1 cofiniteness, C2 cofiniteness, and Cn. Oh, so right. So C2 implies C3, C4, and so on. There are C1. So we have some results that on genus 0, for instance, many things are coherent, but just because it's genus 0. C1 sometimes is enough, which is a slightly weaker condition. But in general, yeah, they are not always finite dimensional. So there are examples, for instance, in the case here. So here I said that you have to induce up your module and then take a quotient. You can also construct a vertex algebra where you induce up the module, but you don't take the quotient. You just take this Verma module construction. If you do this construction over MGN bar, for G, I think, bigger than 2, they're not going to be coherent. Yeah, so that's, so in general, maybe some observation. These could fail to be coherent. Another thing I want to say is that in general is not globally generated on M0 and bar. Right? So we, as I said before, the case of Lie algebra is when you have something in degree 1 that sort of plays an important role. And if this is the case, then you will have globally generated vector bundles or sheaves. But we have like numerical examples, like we can compute Chern classes, which I'm going to say next, and we can compute they have some negative properties, so they're not globally generated. So let me just say that we can compute Chern classes. Chern classes of V are given, well, again, if C2 and rational, right? So these are under some conditions we can compute this thing. And the big missing piece here, perhaps, is this connection with Bungie. Right, so I think there are maybe 2 types of people, those who like MGN bar and those who like Bungie, or maybe you like both. And here there's not a clear Bungie side of the story. Because there's not a Lie algebra, so we saw how the Lie algebra somehow played a role. So, so something that one can think about, and this is a project I start, and I was like, I don't know if there is ever a positive answer to this. It's very hard to understand how to give a homological interpretations of this object. Like, do they describe something beyond what I'm giving you, beyond this definition? In some cases, you can. There are a billion conformal blocks, which sort of plays the same thing as like bund gem, like line bundles, or they're in, but in general, it's not clear whether there is a story there. And I think my time's up. Okay, well then I'm done. Sorry. Yeah. Oh, yes. Okay, so maybe I want to say something that the title said conformal blocks from vertex operator algebra, but actually I want to say and more, because maybe you don't like vertex operator algebra, but what you like are decorated curves or just a geometric input and some representation input. So I want to say maybe the message, the construction of these spaces is like, give me some geometric datum where you could sort of attach some representation theoretical input. Is there a way to construct a sheaf on moduli of the geometric object? Right, so you can do this, for instance, in my PhD thesis, and then later Juzu Hong with Shravan Kumar and also Hassan Zelachi, they constructed and we constructed what we call twisted conformal blocks, which describe global sections of line bundles on parahoric, on the model space of parahoric bundles. So you can go in that direction. So you take the Bungie side of the story in your mind, and you think, what if I take a general G? Now it's not vertex algebra, it's more, Lie algebras, but of non-constant. Or you can think about taking maybe not curves. I like curves, but I think Nicola Tarasca, he has some works where he takes maybe a billion varieties, and he can construct analog conformal blocks there. right? One has to be more careful what the representation is here. And another thing that I'm doing together with former student in San Diego, Jacob Keller and Chris Manon, is understanding these on other compactifications on MGM bar. Just take SLN or just your SL2 as your Lie algebra. Can we do conformal blocks on cuspidal curves or on other types of curves? The answer seems you can define them, but they won't be vector bundles. It seems that they really go to infinity at the cusp. So I don't know what this tells us. But there are many directions in which you can go. And this tells us something about these moduli spaces of bundles or curves or objects. This is what I wanted to add in these 2 minutes. Thank you for giving me the time.
Any questions?
Mm-hmm. Yeah, I think it's a preprint last year or this year, but maybe last year. I think you should ask him, not me. Yeah, you should ask him. Yeah, no. Yeah, I don't remember. Sorry, yeah, but the paper, I mean, the preprint is out. So, and this is actually based on, well, yeah, maybe here I said the Virasoro was the crucial Lie algebra, and then there is a metaplectic Lie algebra that plays the similar role, with very different object. It's not anymore vertex operator algebra. Yeah, you can check. I'm sure he'd be happy to hear comments. I don't know. They sort of are associated with different objects. So yeah, I don't know that. I remember Nicola came and gave a talk and we talked a bit about it, but I don't know some of the details. And I think some of the things are still under investigation. Yeah. Yeah, but what we in the MGN world, yes, everything is functorial. Yeah. But what we don't know, for instance, is these twisted conformal blocks live on some modular space of coverings, which naturally maps to MGN or other things. We don't really know the behavior between the twisted and the untwisted conformal block. There are some behavior like pointwise, but not in families. It's not being studied yet. Yeah. I mean, for Hassett, I don't know whether the simple thing is to take the direct sum of the two when 2 points collide, just take the direct sum. This is something I would do. I didn't think about the Hassett space, but my guess is that one can probably do this by defining it when the two models collide, and the algebra just acts there. But yeah, I don't know. I mean, this thing of these other compactifications is some sort of new things but it would be nice to understand where somehow these things originated in, well, when I talk with physicists, for physicists, curves are never nodal. So it's very hard to push this in, to ask what happens. Yeah, it would be nice to know. Actually, yeah, would like to understand how this makes sense. But I don't know yet.
Okay, let's think.
Thank you.